Good morning everybody. Today we are back with rate processes, and today we will start with reaction dynamics. Now, so far we have read, let us see what we have read throughout the series of lectures. We have studied reaction rates and basic rate laws, then effect of temperature on reaction rate, then reaction rate, complex reactions, then theories of reaction rates, then we talked about this kinetics of some specific reactions, then kinetics of catalyzed reactions. We talked about fast reactions, reactions in solution. Last lecture we in last few lectures we discussed, we have given outline and just a brief idea of ultra fast processes. Now we are here with reaction dynamics. Now, before we start with this, we would like to recap few points before going into the details of the subject, Now, few terms will be important here. Okay. Now, one is collision cross section. Okay. Which is the area that is pi d a square or pi a b, pi d a b square of a circle having the radius equal to the collision diameter is known as the collision cross section. Okay. So, say this is A and say this is B, it is little bigger. So, A d A, this is d a b, or maybe if both are same, then it will be d a a. So, if you draw a circle of this type, then area will be pi d a b square. Okay. So, area of a circle having the radius equal to the collision diameter is known as the collision cross section. Okay. So, this is your collision cross section. This is your collision cross section. Okay. Then another term, collision density or collision number. It is capital Z A A or capital Z A B. Okay. This is your collision density, which is often called collision number. Z A A or Z A B is the total number of collisions of type A A or A B per unit time, per unit volume in a system containing only gas or solid molecules of type A or containing molecules of type A and B. Okay. So, collision density is often called as collision number, which is nothing but the total number of collisions of type AA, that is say AA molecule, collision like this, or AB molecule. So, it is the total number of collision per unit time per unit volume in a system containing gas or maybe solute of only one type or maybe containing A and B together. So, it is the total number of collisions. Remember, it is the total number of collisions of type AA or AB per unit time per unit volume. Then collision diameter DAA or DAB. Okay. Collision theory, in simple collision theory, the frequency of a bimolecular collision depends upon the collision diameter DAA and DAB, which in the simplest form of the theory is the sum of the radii RAA or RAB of the colliding molecules, as I spoke over here, as I told over here. Okay. So, sum of the radii, this radii and the other radii. Okay. The collision cross section sigma is defined as, like I already told, it is pi DAA or pi DAB square. These expressions are also applied to equivalent quantities derived from the experimental results. Therefore, collision diameter, collision cross sections, they are connected by a factor, I know pi DAA square or pi DAB square, and DAA and DAB are the collision diameter. Okay. Elastic collision, a particle, that is an atom or a molecule, can undergo a change in its state of excitation as a result of collisions with other particle. Okay. State of excitation means, suppose because of collision, say this molecule was in the ground state, say, and say this molecule is in the excited state. So, when they collide, maybe because of energy transfer, the energy of this can be transferred to this. Okay. So, if that energy is absorbed by this black one, this one, then it may be excited. So, its state may get changed. Okay. So, its state of excitation as a result of collision with other particle, okay, may undergo change. In an elastic collision, an exchange only of the kinetic energy takes place between the colliding spaces. So, there is a kinetic energy exchange, and in an inelastic collision there is an interchange between the kinetic energy and the internal energy of the particle. So, some portion of the kinetic energy has been converted to the internal energy, okay, because of some internal arrangement. Okay. So, internal energy change means something else. It is not exactly this kinetics case, that kinetic energy that initially it was static, say a molecule is hitting, then it becomes static and it goes away. So, it is a change of translational kinetic energy. Okay. So, inelastic and elastic collisions are different. Okay. Collision frequency small z a. The collision frequency is the number of collisions z a per unit time experienced by a single molecular entity on collision with molecules of type A. Okay. And collision density Z, capital Z A or Z A B is the total number of collisions per unit time per unit volume in a system containing only gas or solute molecules of type A or containing two types of molecules A and B. The collision frequency factor Z, small z A or small z A B is the collision number divided by Avogadro constant L and divided by the square of the concentration or the product, I mean square of the concentration for AA collision or the product of the concentration for AB collision. Okay. So, square for AA and product of concentrations for AB collision. In simple collision theory, the rate constant of a bimolecular reaction between A and B is expressed as rate constant K is P AB, then Z, small z A B, that is the collision frequency factor, then e to the power minus E by R T, where P A B, caps P A B is the steric factor, allows the fact that even when energy requirements are satisfied, all the collisions are not effective. Suppose suppose for exchange of atom maybe in this direction along this axis, if that is the requirement, and suppose collision occurs in this way, then exchange is not possible. So, this collision will be ineffective, but this collision will be effective. Okay, so, it is the steric factor that allows the fact that even when energy requirements are not satisfied, all collisions are not effective. Okay. So, steric requirement, specific orientational requirement is important. Line of centers model, this is a form of the collision theory of chemical reactions in which the assumptions is made that a reaction can only occur if on collision the component of energy along the line of centers of masses of colliding particles is greater than a particular threshold energy. Okay. And another thing is important, which is called the steric factor, and this is a factor introduced into simple version of collision theory of reaction to take care of the fact that reaction probability depends on the mutual orientation of the reactant molecule, as I mentioned over here that a specific orientation is needed. Not all orientations are effective in giving a chemical reaction product. Okay. So, these are some points that we may be encountering. So, that I just told you. So, these are taken from Pure and Applied Chemistry of this volume, and it is the copyright of UPAC. Okay. So, let us recap the collision theory again. So, that simple collision theory. Collision theory. Okay. Simple collision theory, reaction occurs by collision. Reaction by collision. Okay. And collision energy must exceed the barrier height. Okay. So, the reaction rate can be written as collision rate and fraction of collisions times a factor f, which represents the fraction of collisions with energy exceeding the barrier height, that is E0. Okay. So, the reaction rate is written as, which is written as, normally reaction rate is written as K, which is a function of time times say concentration of A into concentration. It is the normal way of writing from the chemical kinetics point of view. Okay. And your collision rate is basically capital ZAB into A into B, concentration of A into concentration of B. Okay. Now, this is the starting point of our discussion, that we will start with simple collision theory, then we will progressively move to the other models. Now, what is the need for studying reaction dynamics? Now, chemical reaction, why chemical reaction occurs? Now, chemical reaction has got a connection with chemical reactivity. Okay. Chemical reactivity means, chemical reactivity means how reactive a substance is. the substance may be highly reactive, may be less reactive. Okay. So, reaction dynamics has got this thing, that understanding of, means it tries to relate some aspects of chemical reactivity, that is aspects like understanding of chemical reactivity, predicting, and also controlling. So, how can you control reactivity? How can you predict that this reaction, predict about the reaction, and also it gives us understanding of chemical reactivity. Okay. Now, we will be curious to know about the nature of forces that play in chemical reaction. Okay. So, the thing is that chemical reactivity we wanted to, so reaction dynamics has got the connection, like we wanted to understand, predict, and control chemical reactivity. And for this we are curious to know the nature of forces that are there. So, we also would be happy to know the nature of forces. Okay. Forces that play crucial role in chemical reaction, in chemical reaction. Okay. And also when it is the question of chemical reaction, that is as I told you that that a minimum amount of energy must be there to cross the barrier. Okay. That is, all collisions are not effective. Certain collisions with having energy greater than the barrier height can cross the barrier and lead to products. So, when it is the question of barrier, then naturally question of potential energy surface comes. So, we would like to know the nature of potential energy surface as well. Okay. So, the principal idea is that the very basic idea is that the reaction occurs by collision, and collision energy must exceed the barrier height, otherwise it will not cross the barrier. So, it is an activated barrier crossing process. Okay. You have got your reactant and you have got your product. So, it will not come directly from here to here, from here to it will not come directly. So, it will come via a barrier to here. Okay. So, now at when collision energy is say given by a quantity say E t, okay, and if that corresponds to a relative velocity between the colliding entities, okay, colliding entities like this. So, relative velocity, if that corresponds to, I mean that is written like C relative, okay, then reaction rate, I mean reaction rate can be written as rate of reactive collision, okay, because collision rate will determine the rate of reaction. So, rate of reactive collision, okay, those collisions which are reactive, not all collisions give rise to product, Okay. Rate of reactive collisions at velocity c relative into the fraction of collision, that is into fraction of collision that are effective into f. Okay. I mean fraction of collisions, those are effective. Now let us draw, I mean which one is, I mean when there is a question of collision, then maybe in some cases they will collide, in some cases they will just touch, or maybe just miss, or maybe a true miss. So this is your one atom, and of course this is the idea is that here we have to think that these reactants are rather structure, they do not have any specific structure, maybe like a hard sphere, okay? And reactants are having radii R A and R B. So basically what is happening, that it is like you have to draw, it is you draw a cross section, okay. So and you draw a cylinder like this also, okay. So if your second molecule or second atom, I mean the reactant, okay, is here, I mean its center is either here or inside, then there will be collision, but if it is just outside, then it is just miss, okay. So those basically if it is like this second structureless entity, so this will not hit, there is a difference, okay. So that means this collision cross section is sigma c, which is equal to pi d a b square, okay. And this is the relative speed, okay. So that means this length is nothing but c rel, and this c rel is equal to at a given temperature, it is square root of 8 k b T by pi mu, where mu is the reduced mass of the system, that is m a and m b, okay. So rate of reactive collisions you can write in this way, rate of reactive collisions equal to some k designated at C rel, concentration of A and concentration of B, okay. So now Kc relative, this is, okay, this is number of reactive collisions which is nothing but Kc relative, which defines the reactive collision volume swept out per unit area, okay. So Kc relative is nothing but your C relative into sigma, okay. So this corresponds to the reactive collision volume, okay. So this corresponds to reactive collision volume, okay, where this is the collision cross section, okay. This is the collision cross section characterized by C relative, I mean at C relative, okay. Now next comes the point that Fc relative. Fc relative, I mean there is a fraction, we define another quantity Fc relative, okay, is the fraction of collision with velocities in the range c relative and c plus dc relative. That is if the velocity lies in the range c and c plus dc, of course c relative and c plus dc relative. So, c relative and c relative plus dc relative. We just would like to know, what is the fraction of molecules, okay, or what is the fraction of collision in this relative speed range, that we wanted to know. So, in that case we have to use the Maxwell's velocity distribution, that if c relative dc relative, okay, which is equal to, you can write in this way, mu by 2 pi kbt to the power 3 by 2, it is a 3 dimensional case, that is why it is 3 by 2 e to the power minus mu c relative square by 2 RT into 4 pi c square relative d c relative, okay, and it has got, if you plot, it will be something like this, okay. This is your c relative and it is f c relative, okay. Therefore, actual reaction rate when relative velocity is c relative is given by reaction rate at real velocity, relative velocity c real is given by minus dA dt is equal to k c relative into B into f c relative. So, this is basically your reactive collision volume, okay. The thermal rate constant is obtained by averaging, this one, this thermal rate constant can be obtained by averaging this one, which is nothing but c relative and sigma c relative, okay, and that has to be averaged over Maxwell-Boltzmann distribution. So, therefore, average kT can be written as integration from 0 to infinity, that is we are integrating for all the speeds, okay, c relative into sigma c relative into f c relative dc relative, okay. So, this is your probability function, this is your quantity, and this is the integration variable, okay. So, that will give you the the average thermal average kT, okay. And of course, the denominator should have a normalization constant. So, and generally normalization constant we do not write because it is taken to be normalized to 1. So, that is why we do not write the normalization constant in the denominator. So, it is the expression for the thermal average rate constant. Why thermal average? Because it has to be averaged, okay, averaged over c relative, because there are number of relative velocities, not all relative velocities are effective. So, this relative velocity will range from 0 to infinity, okay, and temperature means it is a measure of mean random translational kinetic energy. So, it is a randomly distributed, okay, and this kinetic energy, you know, it is a random thing. So, therefore, you have to think of all the possibilities, and you have to integrate over the entire range of C, and this is your probability function, that is probability of having a speed from, you know, from value C to C plus dc is given by this. So, this probability takes care of the fact that which speed is most probable, which speed is less probable, and so on. So, that is why it is the right average quantity. Okay. Next, we will see some we would like to talk on some state result properties. Before that, for this particular topic, let me give some, you know, references, like book by Raphael D. Levine and other books I already shown in the first few lectures, plus another book by Tutorials in Molecular Reaction Dynamics in Molecular Dynamics by edited by Valence et al. Valence and another author. Okay. It is available in Oxford. Okay. So, that you can consult for this particular piece of topic, that is reaction dynamics, in addition to this book by Raphael D. Levine and other books I referred earlier. Now, state result properties. Okay. Now, K, let us consider one reaction K plus HCl in the Vth vibrational level gives rise to KCl plus H. But standard enthalpy delta H 0 bar is 4 kilojoule mole inverse, and when V is equal to 1 for HCl, the energy is, the corresponding energy is 34.5 kilojoule per mole. Now, if you put this energy, okay, if you put this energy to HCl, thereby giving rise to vibrationally excited, okay, to generate the vibrationally excited HCl, then it has been found that rate is increased, the rate is 100-fold increased. Okay. But if you put this energy to the translational degree of freedom, then the rate has been found to be 10-fold increase, okay, only 10-fold increased. So, what can you say about it? Means what is the conclusion? Okay, that vibrational energies for the reaction to occur, vibrational energies are more important, okay, than the translational efficient. I mean, vibrational energies are more efficient in promoting chemical reaction than translational energy. So, you recall one thing, that this theory of absolute reaction rate, that when reaction occurs, then one bond is say formed and another bond is broken. So, the bond which is broken, okay, the bond which is broken is required to undergo a low frequency large amplitude vibration, so that that particular low frequency vibration is converted to translation. Okay. So that is why again here from this example you can think of that vibration energy could be more important, and of course, it is 100-fold increased and in another case 10-fold. So vibrational energies are more efficient in promoting the reaction than does translation energy. That is, you supply energy to translational mode, reaction rate increases. Collision is more, of course collisions are more, but maybe if you supply to the vibrational degrees of freedom, maybe it is increased more. Okay. That is, if you increase the energy to the internal modes like not the translation vibration mode, then it happens. Another example, hydroxide radical plus H2, V is equal to 0 1, giving rise to H2O plus hydrogen. Now, if you excite vibrationally this hydrogen, excite hydrogen vibrationally, then rate constant has been found to increase by a factor of 100. Okay, that is, which is basically K T, V is equal to 1 is of the order of K T, V is equal to 0 into 100. Okay. But if you excite this spectator, this OH, okay, vibrationally, then it has got it does not have that much of effect. Okay. Again it says that vibrational excitation is sometimes very efficient in promoting the chemical reaction. Okay. Okay. Now, think about another reaction, that another example, O plus Cs giving rise to CO, different vibrational level, plus S. Okay. And if you plot probability V prime and f V prime, then maybe it maximizes at some higher value. Okay. So, there is a population inversion in carbon monoxide, okay, vibrational level, that is your product is carbon monoxide. So, there is a population inversion, that is which is not discernible at ordinary temperature. Okay. So, that is ordinary temperature says that Boltzmann population, that if the higher level is there and if the energy gap is more than thermal energy, that is kT, then population will be less. Okay. That is lower lower levels will be populated more compared to the higher levels. Okay. So in that case the system is not under thermal equilibrium. Okay. So reactant energies can influence the course of reaction. So reactant energies can influence the reaction, and the products which are formed that may not follow the Boltzmann distribution, products may not follow Boltzmann distribution. Okay. And we would need to prove the population over the product states and control the populations in the reactant states. Now, for example, one thing is important, that velocity, that is important thing is its magnitude and direction, and vibrational and rotational energies, these are nothing but the internal degrees of freedom. So, that is important orientation factor, that is another important thing. Okay. Now, the examples which we cited, like 3 examples over here, clearly demonstrates that that reaction cross section is dependent on velocities of your reactants, then the vibrational and rotational states of your reactant, and also maybe the orientation is very important. So, that part I will be coming to later on. So, vibrational rotational state and this velocities with which it is colliding is very important. Now, next we have to think of, when it is the question of collision between two entities having no specific structure, maybe two balls are colliding. Okay. So, the collision may be elastic, collision may be inelastic. So, we have to think of the conservation, because somehow it will be conserved. Maybe if the collision is not elastic, so some means energy may be transferred in some other degrees of freedom, or in some other way, maybe in the form of heat or else. Now, consider a reaction like A plus this giving rise to AB plus C. Okay. Now, conservation of energy, conservation of energy says that, what does it say? The energy which is available. Okay. Now, for a particular reaction, suppose you have got your reactant over here and maybe product over here, and it is going from reactant to product this way. Okay. So, and this is the total energy, say. Okay. So, is the total energy. So, available energy you can write in terms of E available is E total plus E translation plus E vibration plus E rotation, minus heat of reaction, enthalpy of reaction. Okay. So, basically this heat of reaction, you can write in this fashion, maybe this energy, maybe if it is distributed over here, then maybe E prime translation plus E primed vibration plus E primed rotation. Okay. So, what is happening that because of this process from A to B, so energy must be conserved, that is this side energy and that side energy must be conserved, plus something, maybe plus heat, plus minus heat. So, if you add up here, then it must be conserved. Okay. So, conservation of energy, that is it is very important for such process to occur. Okay. And of course, it may be computed either in terms of reactants or in terms of products. Okay. Another important thing is that conservation of other quantities like angular momentum, that is also an important thing. So, not only energy conservation, but also energy conservation, it is applicable as also the other conservation principles like angular momentum, conservation of angular momentum. Is important. So, what about rotation? Now, thing is that we are talking about A plus B C giving rise to A B plus C. Okay. So, this has got the rotational angular momentum. Okay. So, J B C is equal to root over J into J plus 1 in H cross unit. Okay. Now, so this has got the angular momentum. Now, in the same way, orbital angular momentum will be given by, total angular momentum is nothing but it is your rotational, and orbital angular momentum L will be given by root over L into L plus 1 in H cross unit. Okay. And which is basically your mu into C relative into B. Okay, B is the separation between, say you have got your B, this is C, and say this is your A, which is coming in this way, A with C relative and separation B. Okay. So, M R, it is basically mu R into velocity, relative velocity. So, total angular momentum. Okay. So, rotational angular momentum is this and orbital angular momentum is this. So, in computing the orbital angular momentum, you have to make use of this diagram. Okay. So, total angular momentum is given by J total is equal to J B C plus L. Okay. So, this way orbital angular momentum and total angular momentum, they can be they can be used in orbital angular momentum and your rotational angular momentum can be used over here. Okay. So, and of course this is your reactant side, and for the product side what is happening, that product side it will be corresponding, this value will be J A B and plus say L prime. So, these two will be equal. So, conservation of orbital angular total angular momentum will be there. So, this way we have to consider the conservation of angular momentum. Okay. Like here in case of your energy, so your reactant side is like this. If you think of energy, that this is your reactant, this is your product. Okay. So, maybe this corresponds to translation, rotation and say vibration combination, and maybe this corresponds to say translation primed, rotation primed and vibration primed. So, we have to make use of this equalization, and of course, this is your heat of reaction. Okay. So, this is our delta H of the process. So, this way you can equalize this and that, the back in the left hand side and right hand side. Okay. So, that is about the conservation laws. So, we have to think of the conservation principle. Now, I will stop today, and maybe next lecture I will take up the forces and potential energy factors and energy factors, various potential energy types, I mean potential energy curve for diatomic system, etc. I will take up. So, what we have learned today, let us have a quick recap. That we wanted to start with this reaction dynamics to understand the chemical reactivity, to predict chemical reactivity and also controlling chemical reactivity. We would like to know the nature of forces responsible for the nature of forces that play roles in chemical reaction, and also we would like to know the potential energy diagram which is of a prime importance. We started with collision theory of reaction, right? That collision in gas phase, collisions are responsible for chemical reaction to occur, and not all collisions are effective. Certain collisions are ineffective, maybe energy wise, because that is that threshold energy is not crossed maybe. Okay, so sometimes collision may not be effective. Okay, so and we gave certain examples. We cited certain example that state resolved properties and how vibrational energies are, vibrational excitations are more efficient than translational excitations. Okay, and we gave examples on that. Then we started with conservation laws. It is the energy conservation must be followed, left hand side and right hand side energy conservation must be followed. That is total energy in the left hand side and total energy in the right hand side, that is available energy means total energy of the system. Okay. Translation energy, rotational energy, vibration energy in the reactant side and in the product side. Okay. So, as if this difference in you can think in this way, that your reactant side in the left hand side, your and the product side in the right hand side, what is happening that these are connected by delta H. The difference is called the delta H. So, as if this excess delta H, delta H of the reaction is there with your reactant side. Okay. The moment it is converted from reactant to product, this energy which was there is released in terms of heat of reaction. So, conservation of energy is there, and also conservation of angular momentum, that is very important, that also has to be imposed. When there is a gas phase reaction, maybe conservation it is, say this is one species, say A, and this is BC, so they collide like this. Okay. So, it has got this your rotational angular momentum and the orbital angular momentum because of this geometry, A and this BC. So, these two together are needed to be considered for applying the conservation. Okay. So, I guess that is all for today. So, next lecture we will take up this potential energy and energy issues, potential energy curve and those things, like attractive potential energy curve, or maybe the potential energy curve that is for, say, maybe this diatomic potential energy curve. will take up that issue, and will proceed further. So, till then, thank you.